By using GStreamer, one of the features that it supports is keeping independent pipelines in synchronization with each other. So we were able to play the audio and play the video, and GStreamer pipeline kept them in sync, what we call lip sync. And below in this slide, you can see a simplified GStreamer pipeline. The parts that I left out is we sometimes set priorities for the various pieces, and we sometimes specify some buffering data to make the data flow through the system smoothly. So basically what we did is, you can imagine the little blue diagram where we had our simple MP3 player. Well, in a similar way, we've got on the left side file source element pulling data off the file system. Then we run it through a QuickTime demuxer to decode the audio and data into two independent streams. And in this case, that means the demuxer has one sync element which takes in the the QuickTime encoded data, and it has two source elements, one for audio and one for video. And we name those, so we have demux audio and demux video. We run each one of those through a queue, and then for the video, we use the video decoder, which is running on the DSP, and then we go through the color space element, which is also running on the DSP. In this case, the data doesn't really have to leave the DSP. It can go straight from the video decoder into the color space without the data getting moved all over the place in the pipeline. And then we created a new element which you can also get off of the show-off site, which we called IPC sync, and that's inter-process communication sync. And what we're doing is we're copying the data to the frame buffer that QT is using. While that video pipeline is running, we also have the audio pipeline, which is using the audio decoder that is running on the DSP and then goes to the ALSA sync in a similar way of our simple MP3 player. So that is the pipeline that we use for, in show-off, for handling playing version running on the digital signal processor. Next slide. So the thing that I love about the HawkBoard is it's not only useful for some of these, what I think of as consumer electronics, audio and video related applications, but it also has some great IOs like the programmable real-time unit that make it interesting for use in a more industrial environment. So for example, let's say that there's an expensive piece of equipment that has a rotating shaft and you are developing a project for monitoring shaft vibration. So you're trying to detect whether a bearing is about to fail and turn off the shaft, stop the shaft from rotating before the bearing actually fails. So you might have some different types of sensors that you're using to pick up on indications of a potential shaft failure. So you might have some type of rotational sensor, you might have a vibration sensor, you might have a microphone because you're trying to pick up loud squeaks or some other unanticipated noise. And so you can imagine on your HawkBoard, you have these streams of data coming in. Essentially, you're going through an audio to digital converter on various sensors. And let's say you have 3 streams of data coming in. And now, instead of streaming the data out, what you're trying to do is run it through a DSP algorithm that says, is there a potential problem or is it okay? And so you can imagine we have 3 iUniversal DSP algorithms, and each one is processing data, one from the rotational sensor and one from the audio, the microphone. And you're running your custom DSP algorithm, actually 3 algorithms, independently of each other on those 3 streams, trying to detect, is there an issue with this rotating shaft? So your algorithm would understand the type of data that's being received and have some logic in there to say everything's okay or it's not okay. And then you might start logging some of the concerns, or if you think, hey, this data doesn't look right, you might save that portion of the data, not all the data you're capturing, but just the data that looks suspicious to the hard disk, so that if you do give a warning and say, turn off this machine, we think the bearing's about to fail, that you have some historic data that said, here's what we were seeing that caused us to believe the bearing is having problems, and then that can be post-processed, perhaps in a little bit more detail than what you're doing real time. And then let's say that you have some detection. You detect, hey, we think something's going wrong. Well, what are you going to do? Well, you can use one of the GPIOs on a HawkBoard to control a switch which maybe shuts down the machine, or if the machine can't be shut down at any time, it has to be done so in a controlled way. Maybe you use the network connection to send out what becomes a message to someone's pager or an email. You might use the network connection for doing some logging, etc. You might connect up to the VGA display to give some type of status of how it's going, so you can have a real-time status display. There are just so many wonderful IOs on the HawkBoard that would allow you to provide lots of really good feedback in different ways for this type of application. So you can hook up sensors, data that's streaming in from sensors to your HawkBoard. You can have algorithms on your HawkBoard that allow you to process that data. And then you have ways of saving the data and communicating out to the rest of the world, everything's okay or a problem's been encountered. And you can do that all with your very affordable HawkBoard and the software that is available for your HawkBoard. Next slide. So what does your algorithm look like? So for those of you who love to program in C, here is a simple example of the code that would be running on the DSP that supports the iUniversal format. So there are basically two parts. There's a control part that allows you to pass out-of-band data and get out-of-band status with your DSP algorithm when you follow the iUniversal format. And then there's the data processing. So this first slide that we're looking at shows the control portion. And basically, you have to support an API that gets called when a control message is coming through. And this control message is identified by the command ID. And in this case, I gave a simple example where I support the get version, where I can report the version number of the algorithm running. You can add your own custom IDs, and you can look at the iUniversal spec to see all the different IDs that are defined. So you have an API that you implement that can handle the various commands that can come across the control request, the control channel. Next slide. That one I had a couple. Yeah, two forward.
So what slide would you like?
This one says control the next one.
Next one?
Which should say. I added that slide and forgot about it, Lori. I'm sorry about that. So here I'm even giving you a pointer to when I just said you can find out that information by looking at iUniversal. If you go to the TI wiki and look for iUniversal, you'll find the Getting Started with iUniversal, which is describing in much more detail than what I'm going over right now. Next slide. I'm missing my one that says process. I see. Can you go back a couple? That was the first slide. One right there. So in addition to the control, you need to have a routine that actually processes the data. And the way that this works is you're going to receive a pointer that contains buffers coming in to your DSP algorithm, and then you're going to operate on that DSP on that data using the DSP and put it in output buffers. So in this case, for the process routine, this is a do-nothing routine that simply copies the data. It's an identity routine. It copies the input data to the output data, and then follows the iUniversal standard to indicate the status of the input and output, an OK indication. So with these two functions, the control function and the process function, you put those in a data structure related to the iUniversal functions, and that's what we use with the other DSP algorithms that make up the codec to tie them together and know how to access your particular functions that have been put into the DSP to bundle up your algorithm. So we have a process API and a control API, and together we can bundle those as an iUniversal DSP algorithm.